Hello friends, in this video we are going to see the importance of casting in Java. We will learn how we can cast between primitive types and cast between objects. Casting between primitive types. So in this example we are going to do some type casting between primitive types. So first we will know about the basics of the space required for byte, integer and long, because that's what we are going to use in the sample. In Java, int requires 4 bytes, long require 8 bytes, and there is a data type called byte. It requires 8 bit, or we can also call it occupies 1 byte. 8 bit is 1 byte. Java supports implicit casting as well as explicit casting. In implicit casting, Java performs the casting between the types. So user no need to specify the casting. So it is performed by the Java compiler itself. Explicit casting is done by the user. So Java doesn't perform such a casting since it thinks there may be data loss or some problem, so it foresees some problem. That's why it leaves it to the user to cast. So it's up to the user to cast those objects or primitive types. It's called explicit casting. In the below code, we're having an example for implicit casting. If you see, first we declared an integer. Also we initialized it to a value of x. Then we have a long variable t. Then what we are doing, we are trying to save the content of integer x into the long variable t. So here the data moves from the space allocated for integer to the space allocated for long. Since we know that long is 8 byte and integer is 4 bytes, there will be no data loss here. So Java performs the casting since it is safe. So we call this as implicit casting. When the target is not having the room, the coder should do the type casting. It is called explicit casting. Now let us see the example for explicit casting. Int x long t equal to 25. So the first line is integer declaration. Next, in a long variable t, we assign a value of 25. Then we are performing a typecast. So here the int in between the parentheses is called explicit typecasting. So here the user states that I know that long will not exceed 4 bytes. Since I declare the value and at this stage of coding, I know that it will not exceed that value. Later when I perform calculation, it may go beyond the 4 byte. But at this stage, it will be definitely less than 4 byte. So that way, if developer is sure about it, they can perform typecasting and they can store the content of long in an integer variable. Then they can use the variable x for their logic. So if we remove this explicit typecasting statement here, explicit typecasting is placing the type in between the parentheses. So if we remove that, Java will complain that you cannot perform such a casting. Why? Because long is 8 byte and integer is 4 byte. So suppose if your long value is holding a big value that cannot be accommodated in a 4 byte, then there will be a data loss. Okay, let us explore this in Eclipse. Here is our Eclipse. We will go to the main entry. Just for experiment purpose, we will for now comment out this code. So I'm right clicking it, then I'm going to source, picking a toggle command. Now we'll place our code. First we will experiment implicit typecasting. So this we already saw in the slide. Same thing I'm doing here, and I just kept one println statement. So if I execute this, you can see X get printed. First of all, we see there is no error. Then at runtime, it prints the value of time. So here there is no problem in the typecasting, and this casting is performed by Java. So even though user doesn't specify any casting, Java performed that casting, so we call that as a implicit casting. Now we will see explicit primitive conversion. Here there is no data loss. Why? Because int is 4 byte, so it can store value more than 400. So for example, if I go to calculator, since integer is 4 byte, this is 1 byte, 2 byte, 3 byte, and for the 1 bit I am leaving it. So if you count here, so I'm using just a 31 byte only. This is 1 byte, 2 byte, 3 byte, 4 byte, 1, 2, 3, 4 byte. So let us cut down these 3 ones. Then, so this is exactly a 4 byte, but this last bit is used for sign, plus or minus sign. So we have to eliminate that also. So if you see decimal, so this is the maximum value an integer can take. Here this 400 is definitely less than that, so here we are doing the explicit typecasting. So let us remove this, and if I save, you can see an error get displayed. The error states that type mismatch cannot convert from long to integer. So that's what Java is giving. So when user places that, I know what I am doing, I want to convert this long value to integer and I want to store that in X. So if that's the case, then once I save, you can see that error is gone. Then Java will allow it here. So I'm just printing the content, it will show 400. So there is no problem in this explicit typecast. Now we will switch back to our original perspective, I mean the coding perspective. Then we will experiment the third part. Here, if you see, there is a data loss. Why? Because, let me paste it in Eclipse, then explain. Here, we declared a variable called X, and the type is byte. So we know that it can hold only 8 bit. So including one signed bit. So if I open the calculator once again, So this is 8-bit. Since 1 bit is required for plus or minus sign, I am removing that. So this is the maximum value. On the positive side, one can hold one. For safer side, we can take 126. So here 400 is a positive 400 is definitely more than 126. So now here we are asking to cast the integer value and try to store that in a byte variable. So this 400 definitely exceeded 8 bit. So let us see that. So I'm in decimal mode. I'm typing 400 here. And if you see in binary, up to this it is 8 bit. So if we use 7th bit itself, it is not correct. So here we are going to 9th bit to hold the value 400, but byte is just 1 byte. 8 bit only it can use. So this is what called data loss. So we lost this one, then we are storing something in the signed bit that is also not valid. So since the user asked for typecast, Java permitted that. So if we remove that, it will be throwing error here. It says a type mismatch, but since the developer told I want this cast, Java allowed it. Now we see a data loss here, and let us print the output, and you can see what is the data loss and what value it is printing. If you see, it prints minus 112. Okay, now let us go back to our slide. So previously we saw the typecasting between primitive type. Now let us look at casting between objects. Java performs implicit casting when the objects involved are from inheritance tree. So in our example, we already saw an inheritance example. C car is the base class for C BMW and Ford objects. So we can cast between the object C car and C BMW or C car and Ford. In our example, C car is the superclass and Ford is one of its subclass. Now look at the example below. Here first we declared a variable called car1 and its type is a C car. Next we are creating the Ford instance, then we are storing that in a reference Ford1 and its type is Ford. In the last statement what we are doing, we are assigning the Ford1 to car1. That means we are handing over the Ford1 reference to car1. Here the type is different between left hand side and right hand side. In the left hand side, the target is C car. Here size required for the target is less than the source. That means the source is Ford type. Since it is inherited from C car, definitely it needs more room to contain the data compared to C car. But the C car is having less room. I mean the C car, it will definitely have less room compared to Ford. By looking at the inheritance tree, Java does implicit casting when target is up in the inheritance tree. So if you see, the C car is at the top and C Ford is in the bottom in the inheritance. That means C car is the superclass and Ford is the subclass. If some more car a special type of Ford car is inherited from Ford, the casting is still valid. So if we create an instance of that third level special Ford type, and we can still store that in C car. Why? Because C car is up in the inheritance tree. So that's what here it is stating. So implicit casting is done when target is up in the inheritance tree. So that's why here Java doesn't give any error and it performs the type casting implicitly. Now look at the example below. Here we are creating an instance of C car and holding that in a reference called car2. Then we just declared a type Ford and variable is Ford2. Then we are handing over the car reference which is stored in car2 to Ford2 reference. Here the source is C car and destination is Ford. So Java throws error here. Why? Because the source is, the destination is not in the inheritance tree at upper level. Here size required for the target is more than the source. So unlike primitive data type, here the size is not important. Why? Because Ford2 and car2 both is going to hold address of the heap. So here in the casting, type is not important. What is important is where the source and target stays in the inheritance tree. So that's what important. So the heap size is not important. That's why here we are saying the size required for the target is more than the source, but still it allowed the casting because of the reason just now we talked about. Why? Because the content is actually address, so the size will be always equal. Depends on a 32-bit program or 64-bit program. There will not be any difference in the size, but the content it points at, that means the heap location, we may have different size. Alright, since destination is down in the inheritance tree, here Java throws the error. To rectify the error, we can do explicit typecasting as follows. Here it is Ford2 instance, and if you see here, I am placing the explicit casting here. We are placing a Ford in between the parentheses. Now Java leaves it to the coder. The explicit casting actually Java leaves it to the coder, so it is coder's responsibility to make it foolproof. You see here, even though Java doesn't throw error here, what we are doing here is wrong, and we will see that when we are proceeding with this video further. Now let us explore this in Eclipse. So here is our second part. What we will do, first we will place this in Eclipse and explore. So I'm reverting back my comment. Now if you see, Java performed implicit casting on this particular step. It doesn't throw any error. Now if I try to perform the casting the other way, if you see, car1 is up in the inheritance tree, C car Then food is derived from seeker. You see, food is derived from seeker. That's why it allowed the casting previously. Now, if we save it, we can see there it says that type mismatch cannot convert from seeker to food. But if a developer puts like this, so the coder asked for the typecasting. So they say that I know what I am doing, so convert this car to food. So what Java says, it doesn't complain about this. But we will get error at runtime. We will see that later. For now, you can see with the explicit typecasting, user is taking the risk of the object conversion and they are opening gate for runtime error. So they should be careful when they are casting it explicitly. Previously we saw data loss in the explicit casting. So now here there will be runtime error that we will see later, and the point here is when you are doing a typecasting, you should be aware that it won't break the code. Alright, now let us go back to the slide and we will study further. So to experiment further, let us first add two methods to our food class. The methods are start food car and stop food car. So these are the two methods we are going to add for our food class. Then we will add similar two methods in our BMS. It's not BMS, it's BMW class. So we will have these two methods in our BMW class. So after adding this, we will explore the behavior of implicit and explicit casting. So we already provided an example in the previous slide, and we will experiment further with these two new functions added to the classes. Okay, let's add these methods in Eclipse, then we will come back to the slide again. So now what we will do, we will go to our CBMW, then we will open our seafood. First we will modify the food car and we will add these two methods. We will add it after the constructor. So here is the outline view. You can see that two methods get added here, start car and stop car. It just prints starting the food car and stopping the food car in the console output window. Next we add these two methods to our BMW. So that's all. So if you see, the food car has a private member, then a constructor, then start and stop method. After that one overridden method print. The same goes for BMW also. It has a model number, part number 1, part number 2, a constructor, then start and stop method. After that there will be a print method. Okay, we will go back to our slide once again. So implicit object casting, we already saw an example. First we will take implicit type conversion, which we already saw. So I think no explanation is required here. See, the statement we already saw. Now look at the diagram here. What happens? The object what we are creating is actually a food object. You can see the new keyword, new food. So that's what we are creating in the heap, and in the picture it is marked with green color. So you can see the actual object will contain all the members, model, food, print, start food car, stop food car. These are all the member of the food object. Then it has the inherited member, car name, max speed, C car constructor, and print. So these are all the inherited member. In the third statement, if you see, Java performs typecasting. So the actual object in heap is in green color. That means it has a food object with all member available. But the reference pointing to that heap location is C car reference, car1. The type is a C car. So now we have access to whatever is marked in gray color, even if the object is a food object. The actual object created in free store is food object, because the new keyword, in the new keyword we are asking food. So the food object will constructed, and memory is allocated for food object, and that will get stored into the heap. The climbing object type is a C car. That means here we are handing over the food1 reference to car1. Car1 is actually C car. So that's what we are saying. So the climbing object means the object which try to access that heap location. So we call this as a climbing object. And the climbing object type is C car. Since the reference type is C car, we cannot access the function start food car, stop food car. So you can see that in the picture. You can only access whatever is marked as a gray color here. Since that is the object type, we are referring that's the object type we are using to refer the actual food object. Even though food object contains the model, start car and stop car, with this reference car1 we don't have access. But if you see, the base class is having the print method, void print, and food object also, the derived class. There are two print methods you can see, one in the gray area and another one is in the green area. The green area void print belongs to the food object, and gray area void print belongs to C car object. Since the method signature is same, since it comes under the method overriding, when we make a call through car1, the print method of overridden version, the method in the green area void print, that will get called. So we already saw this in the overriding example in the previous video. So that's how in the previous video, if you see, it called the derived class method. So this is the reason how it will call the derived class method. At compile time, the void print will get resolved, because the base class also is having the print method with same signature. So this will resolve the compile time. And at runtime, it knows which method to call. Since it is a overridden method, it knows the actual object created is for the derived instance. So it will go and call the print method, even though the pointing type is car1. So explicit object casting. Here, if you see, we placed the food in between parentheses, thereby making the cast explicit. Here if you see, the actual object that we create in the heap is C car. But what we are claiming is the entire food object. Why? Because the destination or the target type here is food, but actual object in the heap is C car. So the green area shows what is the actual object in the heap. But we are claiming that since we did the typecast as Ford, we are claiming that through this reference I can access model. Model is a data member here, you can see that, but which doesn't exist in the heap at all. And we are stating that I can make a call to start Ford car and stop Ford car. So even though the typecasting is allowed, this kind of fatal will be discovered during the runtime. Okay, the actual object created in a free store is a CCAR object. The climbing object type is Ford, so that you can see that in the gray area in the picture. Since the reference type is Ford, Java compiler is not throwing error. If we call start Ford car and stop Ford car, yeah, that is not shown here in the code. We just left at the typecasting itself. Soon we are going to see that at runtime Java will throw error on this statement itself. But as a fourth statement, if you put Ford2 dot start Ford car, Java compiler won't throw any error. Why? Because the reference type is Ford2. I mean the reference Ford2 type is Ford, and the Ford class has method start Ford car. So if you make a call to start Ford car, it won't throw error. But actually you are making a call to a function that doesn't exist at all at runtime. But as far as the compiler is concerned, you are making a call to Ford2, and Ford2 is of type Ford, and Ford class has the method. So that's how compiler sees, and it doesn't throw error. Alright. But on runtime, this will lead to a fatal error as the object in the heap does not have those methods and model data member. Right. So that's the point here. So here the actual object created in a heap is CCAR, which is shown in green, and what we are claiming is more than that. That means we are based on the explicit cast, we are trying to access whatever is there in the green area. So if you start accessing the start Ford car or whatever member in the gray area, you will get error at runtime. Actually, it throws class cast exception at runtime. We haven't explored about the exception so far. For now, you can just know that it will throw class cast exception. We will learn about exception in the coming videos. Okay, now let us explore this in Eclipse. Okay, first we will explore the implicit casting. Copy this code to our program main entry, and I will place it here. Let's remove this. If you see here it is a implicit cast, and car1 is a base class reference type. And if we put car1 dot, we will not see the start and stop car method at all. So, but if we try to, the object is Ford, right? So if we try to make a call to start Ford car, the compiler itself throws the error. If I save here, it says that the method start Ford car is undefined for the type CCAR. Why? Because here even though the object is Ford, the reference is a CCAR type, and if we try to make a call to start Ford car, Java compiler will throw error, because Java detects this kind of error at runtime itself. Why? Because it knows what is the type car and it knows that this start Ford car doesn't belongs to type C car, it belongs to Ford, so it throws error. Also, if you see here in this statement, we doesn't get any error because the target C car is up in the inheritance level. That means in the inheritance level, in the sense compared to Ford 1. Ford 1 is somewhat here Ford, and C car is above. That means Ford 1 is a subclass of C car, so this is allowed. Now let us explore the second part. So no compile time error, the error will be at runtime, so we will debug and see. So if I save, it just allows that. Why? Because here we casted it explicitly. If I put a 42 dot, you can see I can access the member start Ford car, stop Ford car. So let me go for a start Ford car. It just allows that member. Why? Because as far as the compiler is concerned, it doesn't look for what is the object created in a heap. Why? Because this will be done at runtime. So when we run the program will create a allocated memory in a heap, then points that heap location with the CCAR2. So this happens at runtime, not at compile time. So what happens at compile time is Ford2. I am casting the car2 as a Ford2. So if I remove this, Java compiler detects that since I am asking that I want the conversion explicitly, it doesn't perform any type checking at compile time because of this conversion, and we are making call to start Ford car. Let us see what happens. It will throw error at this casting itself. Even though we asked for explicit type cast, Java will throw the casting exception. See, dispatch uncaught exception, and this will throw java.rank.class cast exception. C car cannot be cast to Ford. Alright, let us go back to our slide. We will So then when we will use explicit casting, we previously thought that doing explicit casting wrongly throws runtime error. Consider the code below. Here we are creating two objects in the heap. One is CBMW and another one is Ford. Then we are storing these references in object. If you see, object is the base class for all the classes in Java. In our inheritance hierarchy, C, BMW and Ford is derived from C car. C car is derived from object. Of course, C car is derived from object. Now, we are storing the CBMW and Ford references in object. There are two references, one is BMW and another one is a Ford, and both falls under object type. So the object in the heap are cbmw and 4. Most of the Java collections store objects. That means the method, whether it is array or list, whatever it is. Suppose if we have a method called add, it will accept the parameter as object. So what we can do, we can send our BMW and 4. Why? Because the object, the reference type here is object. So that's what most of the Java collection expects. It expects a reference of type object. We can store BMW and 4 in any Java collection which takes object reference type. So most of the Java collection accepts object reference. So we can store our cbmw and 4 in collection by handing over the reference of type object. When we retrieve those stored object, it gives back whatever we stored. So previously we stored BMW and 4 through object reference. So when we are retrieving, it will give back the type as object. So at that time, what we can do, we have to typecast that. So for example, if list.get object, I'm just saying, I don't know, at this time we don't know the methods in the list. We will explore that later, but for now we will assume we will have a get method in the list and it will return the object. So what we can do, we can typecast that to the, explicitly we have to typecast that to a required reference type. So here in the below example, we know that BMW is object type. We can typecast it back to cbmw. Similarly for 4, we can typecast it back to 4 reference. So this is one example where we will perform explicit casting. Here we are not making any mistake. Why? Because the actual object itself is a cbmw. Whatever we created in, let's take the first statement, BMW, I'm casting it as a cbmw. BMW type, reference type is object, but the actual object is cbmw. So if I typecast it back to cbmw, it is valid in this explicit cast. You won't get any runtime error. We will learn more about collection in the Java API video series. So that's all in this video. Thanks for watching. Bye.